Guys, welcome back. This is lecture 12 of the lecture series Signals and Systems. In this lecture, we'll be learning about the geometric evaluation of Fourier transform from the pole zero plot, and we'll see some properties of Laplace transforms and some important Laplace transform pairs. So let's get started. In the previous video, we saw about Laplace transform. So here again we saw two equations. So x of s is the Laplace transform of x of t given by integral minus infinity to infinity x of t e power minus st dt. And we had the inverse Laplace transform given by 1 by 2 pi j integral minus infinity to infinity, and we had actually sigma minus j infinity and sigma plus j infinity, and x of s e power st ds. In these both equations we saw, and we said that we will not be using this equation anywhere. We'll be only dealing with this equation, and if we want to find the inverse Laplace transform, we'll just use the partial transform and try to relate between x of s and x of t. Okay, so now we also saw that the Fourier transform was nothing but x of j omega was nothing but the Laplace transform evaluated at the j omega. So this means Laplace transforms evaluated at the j omega axis. So sigma is 0 here. So using this, now let us see the geometric evaluation of Fourier transform from the pole zero plot, or in general let us see, like, for any given s1, how do we actually visualize this x of s from the pole zero plot. So geometric evaluation of Fourier transform from the pole zero plot. So first let us take a look at the pole zero plot. What do we have here? We have real of s and imaginary of s, and we will have some poles and some zeros, right? Something like this. Okay, so now if we see for complex number x, yes, we actually write it as sigma plus j omega. So this is like the x-axis and this is like the y-axis. And we can't directly add x-axis with y-axis. So it also in some terms acts like a vector. And it is two-dimensional vector kind of. So if we want to do some operations like addition of two vectors, we can perform even in the complex domain. We can add two complex number together in the form of vectors, right? Their x coordinates, which is the real part, will add together and their imaginary part will add together. Here also it is the same. So we have some relation between the complex numbers and the vectors. So we'll just exploit that to get a geometric evaluation of Fourier transform from the pole zero plot. Let us consider a 1-0 system, x of s equal to s minus a. So how do we represent this here? So it has a 0 at s equal to a, right? So let's say this point is a. We have imaginary of s, real of s. So how we want to evaluate it at, let's say, the point s1. So x of s1 evaluating at s equal to s1. How does it look like? s1 minus a. So it is like adding s1 to minus a. So how will it look in the graph? So this will be minus a. It is having a magnitude of a and it is pointing in the negative x direction. So it is minus a. And s1, let's say it is some point here. This is the s1. So s1 will be nothing but this point. So s1 plus a will give me this vector, right? So if I evaluate this at S1, you can see I have a magnitude. So this is like S1 minus A. So I have a magnitude given by S1 minus A. And what is the phase here? This is phi. So the phase is phi. So I have a magnitude and phase. So if I just sweep this S1 from to some other point, then it will help me visualize how the magnitude and phase is changing. So that is what it is doing. So I'll be getting x of S1 and like the magnitude and phase of S1 can be determined from the graph. So this is a location of 0. So the magnitude is directly applied. So what if we have a pole? So x of s equal to 1 by s minus a. So again, if we evaluate this at s equal to s1, what will we have? We'll have 1 by s1 minus a. How will it look? Again, we'll be having a pole at a, and the vectors will be same, minus a, and I have s1, and this part will be s1 minus a. It's like a vector. Again, this has magnitude and phase, phi. But what will be its magnitude? Now we need to evaluate 1 by s1 minus a. So its magnitude will be reciprocal of distance between pole and point S1. So for here it was just the distance, it wasn't the reciprocal. So magnitude here was the distance directly between S1 and A, right? And A is nothing but 0, between 0 and S1. And phase, what was the phase here? It was phi, but it will come in the denominator. When we take it to the numerator, you will get minus phi. So phase will be negative of the angle made by the vector with the positive x-axis. So what about for 0? We already saw it is just phi itself. So this is nothing but be same, will be just the angle, right? Angle made by the vector with the positive x-axis. So let me just differentiate and write it as 0 and the pole. So now for a general rational Laplace transform, what do we have? So we'll have a signal like this, given by x of s is equal to some magnitude m, and we'll have the product of zeros in the numerator. So I equal to 1, 2, okay, I'll put some other s minus beta I, zi, and poles in the denominator, j equal to 1 to p, s minus pi. So what do we do in this case? So first we find the magnitude and phase at point S1 from the respective poles and zeros. Respective zeros and poles. And then what we do? For magnitude, we multiply all the distance from the zeros and divide by all the distance from the poles. And for phase, we need to add them. We add all the phases made by the point, the vectors, alright? The vector formed by zeros and subtract the phases made by the vector formed by poles. So to take an example, if we have this and we have some poles and some zeros, and I want to evaluate at this point S1, let's say. So then I need to consider these vectors. So what will each of these vectors will have a magnitude. So the magnitude, let's say it's R1, R2, R3, R4, and they will also have a phase, right? So let's call it phi 1, phi 2, phi 3, phi 4. So when we have this x of s, so x of s can be written as m into r1 e power phi 1 into r2, sorry, it is zeros, right? So r3 and r4 are zeros. So r4 e power phi 4 divided by r1 and r2 are poles. Phi 1, r2 e power phi 2. And again here, we have to also multiply by the factor and also include the factor m. So we also need to multiply by the factor m. So what will be the magnitude? It will be m r3 r4 by r1 into r2 into e power phi 3 plus phi 4 minus phi 1 minus phi 2. So if you see, the phase is nothing but sum of the phases made by the zeros minus, and we are subtracting it from the phases made by the poles. And the magnitude is nothing but product of all the magnitude of zeros and divided by the product of all the magnitudes of poles, and we also have the m factor. So this is true in general for any point S1. Now for Fourier transform, what do we do? We need to evaluate Laplace transform at s equal to j omega. So we need to evaluate at s equal to j omega. So what will happen? We should take with respect to the j omega axis. So j omega. So these will be the vectors and these will be the respective angles. Okay. So let us see an example. Let's take a simple example. Let's not complicate this. So x of s equal to 1 by s plus 1. So what happens here? And we say real of s greater than minus 1. So what will be my Fourier transform? You can see this 1 by j omega plus 1. Right? And I have one pole at minus 1. So this is the only pole. And let me take this j omega point. Now this will be my vector, right? So this vector I'll name as some r. So it will have a magnitude of r and let's say phase of theta. So r is equal to r theta, r e power j theta. Again here it is like j phi because it is phase. I forgot the j factor. We can include that. Okay. So but since it is a pole, my x of j omega will be nothing but 1 by r e power minus j theta, right? So you can see now when we increase omega, what happens? So initially, let's say omega was here, my pole is here, we had this. Now if I move this to some omega here, j omega 1, j omega 2, omega 2 greater than omega 1, what happens? You can see the length is increasing and the angle is also increasing, right? So my magnitude of vector r increases and phase also increases. Okay. When omega is 0, what was the case? My r was minus 1. So magnitude of r was 1 and phase theta was 0, right? So as omega increases, we have r also increasing and phase theta is also increasing. And how long can r go? When omega tends to infinity, r also tends to infinity and theta tends to, so it will be a straight line which is nothing but 90 degree, right? It will be something like this. So which is pi by 2. So my theta tends from 0 to pi by 2 as I increase omega from 0 to infinity. But what happens to x of j omega, which is the Fourier transform? So it is nothing but 1 by r vector, right? So what will happen to that? So as omega increases from 0 to infinity, x of j omega, the magnitude decreases from 1 to 0 because r is going to infinity. So x of j omega will go to 0. And what about the phase? Phase of x of j omega, again it decreases from 0 to minus pi by 2. Decreases from 0 to minus pi by 2. So using this you can also plot the magnitude and phase spectrum. So you may think like, why can't I directly take the magnitude from here? It's just 1 by root of 1 plus omega square, and I can also determine the phase, which is minus tan inverse of omega. So yeah, for one pole system it is straightforward, but if you have multiple poles, then it is not straightforward to us, right? So in that case we can use this kind of method where we just need to find the individual magnitude and individual phases, and then we can add and subtract and multiply the magnitudes accordingly, and we can determine it easily. So it will provide a good enough estimate for us to do so. So that's why we have discussed this one. Okay, so next let us see some properties of Laplace transform. Properties of So most of the properties we can get it directly from the Fourier transform. But here the one catch is we need to also include the region of convergence, which is important for us. Otherwise the Laplace transform can have many forms, right? It can have many signals corresponding to one Laplace transform. So it is also important for us to provide the region of convergence. So that will be one major difference between Fourier transform and Laplace transform. So the first property again we'll start with is the linearity property. So since it is just an integral, it is again linear. It is similar proof to the Fourier transform. We can say it is still linear, right? So if my x1 of t has Laplace transform x1 of s and x2 of t has Laplace transform x2 of s, and we need to mention the region of convergence. So here ROC equal to R1, so ROC equal to R2. So R1 is some region, I'll say. So if there are some poles and this is this region, I'll call it as R1. So I can describe R1 as sigma greater than some 3, that way. So like this I can define, and R2 also similarly I can have some other region of convergence. So then if I combine these two signals as A x1 of t plus B x2 of t, then my Laplace transform will have A x1 of s plus B x2 of s, and my ROC now should be at least R1 intersection R2. So we know that why R1 intersection R2 comes, because both of these signals need to converge. Even if one of them is diverging, then the Laplace transform will not exist at that point. So we require R1 intersection, both R1 and R2 to be intersecting, so that both of the signals can have convergence for x of s. But why at least is coming? Because when we combine two of the signals, so some of the poles which is causing the region of convergence to be limited can actually go away, right? There can be a pole zero cancellation. So there can be a pole zero cancellation. Not every time, it is might be kind of possibility. So leading to have a bigger region of convergence than R1 intersection R2. So for simple example, I'll tell you, if we combine x1 of t and minus x1 of t, let's say they have region of convergence R1, and this is also going to have region of convergence R1, right? So when we combine them, my actual signal is 0. So 0 is a finite number, right? So it will, when I take the the Laplace transform of it, it will also come to be 0. So this ROC is actually the entire S-plane, right? So this is a trivial case, but let us also see some examples. Maybe one example related to this, how actually the pole zero cancellation takes place. So let us take x1 of s such that it is, so example I'll give it 1 by s plus 1, and x2 of s is such that 1 by s plus 1 into s plus 2, and this region of convergence is real of s greater than minus 1, and this is real of s greater than minus 2. Sorry, here also it is minus 1 because it is limited by this pole. Okay. So now I want to find the Laplace transform of the signal x1 of t minus x2 of t. So what happens here? So if I plot the pole region of convergence for x1, I have minus 1 here. My region of convergence will be this. So x1 of s. For x2 of s, what will be my pole zero plot? Minus 1, minus 2. And this will be my region of convergence. Now let us take x of t equal to x1 of t minus x2 of t. So x of s will be equal to x1 of s minus x2 of s. So this is nothing but 1 by s plus 1 minus 1 by s plus 1 into s plus 2. So the LCM is s plus 1 into s plus 2. So minus 1 by s plus 1 into s plus 2. But numerator is nothing but s plus 1 by s plus 1 into s plus 2. So now you can see the pole and 0 is cancelling. So pole 0 cancellation. So now this combined system has only one pole at s plus 2. So what will its region of convergence be? Minus 2. So it will actually be this entire plane, right? So real of s greater than minus 2. So it is actually greater than what we started with, right? So this is one example, and like it happens usually in many cases for this rational Laplace transforms. Okay, let us now go to our next property, which is the time shifting property. So if you see our time shifting property in the Fourier transform, what did we have? Let's say ROC is R. So in the Fourier transform, we had for x of t minus t naught, we have e power minus j omega t naught x of j omega. So here similarly, we just need to replace j omega with s. So we have minus s t naught into x of s. So if you see this, so this is just coming as the constant term e power minus s t naught, right? For example, if you see in the integral x of t minus t naught e power minus sigma plus j omega t dt. If you evaluate this, like replace the variable, you will get x of t e power minus sigma plus j omega into t plus t naught dt, and we can take the t naught terms outside, minus sigma plus j omega into t naught integral x of t e power minus sigma plus j omega into t dt. So this is the one again defining what the region of convergence is going to be. So but this is nothing but my x of s itself, right? So its region of convergence is also going to be R. Again, to visualize it, if you have this e power sigma t and if you have the signal x of t, so if it is stable for sigma, right? If it is stable for x of t, it is also going to be stable for x of t minus t naught. Even if you shift it left or right, it will still going to be finite and it will converge. So that is the visualization. Okay. So I'll just write here ROC still depends only on x of s. Okay. So this was our time shifting property. So next let us see frequency shifting or shifting in the S domain. So from the duality property in the Fourier transform, we actually derived shifting in the S domain. So let us also see what happens here. So in the Fourier transform, we had e power j omega naught t x of t, which corresponds to a shift of j into omega minus omega naught, right? So here also we'll have e power s naught t x of t. This is L for s x of s minus s naught. But what about the region of convergence? So here let's say the region of convergence is equal to R. So R is nothing but real of s greater than some value, right? Let's say some value or some value. Now my new R prime for this will be nothing but real of s minus s naught greater than some value, right? Because it is the same x of s, s replaced with s minus s naught. So what will this be? Real of s is greater than some value, which was nothing but this R plus real of s naught. So my ROC is nothing but R union real of s greater than real of s naught. Or if R itself we define as some real of s greater than some value, then we can just write R plus real of s naught. Okay. Again, one special case of this is where s naught is equal to j omega naught. it is like shifting in the frequency axis. So what happens in that case? We just get a multiplication by this complex exponential. So that will give a Laplace transform of s minus j omega naught. So what happens? All poles and zeros at A or some A will be shifted to A minus j omega naught. Just shifting in the frequency axis. So everything will be shifted by minus. So it will be shifted to A plus j omega naught. So it will be shifted by j omega naught. Why A plus omega naught? So initially these had poles at A. So it means S minus j omega naught is now going to be having poles at A. So S will be having pole at j omega naught plus A, which is what we have given here. So everything will shift up by j omega naught, and my ROC will still remain R only. Why? Because the real of this j omega naught is 0. So next let us see time scaling property. This was property 3. So my fourth property is time scaling. Again, these derivations are straightforward from the Fourier transform. Like you can take this Laplace transform and inverse Laplace transform, and you can straight away apply this and you will get this. Okay. So time scaling, if x of t has Laplace transform x of s and region of convergence was R, then x of at will be having. So in the Fourier transform we had 1 by a x of j omega by a, right? This was mod a. So here also we have same. We have 1 by mod a x of s by a. But what will be my ROC? So initially s had R. Now s by a should be equal to R. So s will be equal to AR. So my region of convergence will be AR. What does it mean? So what happens if you had initial ROC for x of s is like this. Let's say it was between R1 and R2. So now what will happen to 1 by mod a x of s by a? So what will, if here the poles are at R1, R2. So what will the new poles be here? Here s by a will be equal to R1, R2. So s is equal to AR1, AR2, right? So it will just expand or compress depending on A. So AR2, AR1. Right? So if A is greater than 1, then what will happen? This will expand. So expansion of R. If A is less than 1, we have compression of R. Right? So in the time shifting, what did we have? We had shifting. So the R shifted to R plus real of S naught. So if these were the case, it will shift to R1 plus real of S naught and R2 plus real of S naught. But the region's area remains the same. Here the region will expand or compress depending on the A value. So what happens if you reverse? So which is nothing but a next property. Let's say time reversal. So it can be taken as part of time scaling also, because A can be negative, but just for the sake I am just putting it separately. So x of minus t. So this is nothing but, so if you take the Fourier transform, like the Laplace transform, for x of t you had e power minus st dt. So if you replace t with minus t, what will happen? The limits and this dt sign change will remain same, like they will cancel out each other. I'll get x of minus t e power st dt. So to bring it to the form of Fourier transform, like the Laplace transform, what should I do? I should replace s with minus x. s. So s of minus s is nothing but x of minus t e power minus st dt. So x of minus t ka Laplace transform is x of minus s. And what will be ROC? It will actually be minus r. Why? Because now if it is at r1 and r2, when you take a equal to minus 1, it will become minus r1 and minus r2. So it will just flip around, right? So I have represented by minus r. So next let us see the property of conjugation. So what happens if we conjugate? So let's say x of t has Laplace transform x of s with ROC equal to r. And now I want to find x conjugate of t. So again similarly I'll take x of s is nothing but x of t e power minus st dt. Now to get conjugate, I take conjugate on both sides. So I'll get x star of t e power minus s star t. Because s is complex and t is real, it will not get affected. So then to bring it to the form of e power minus st, what should I do? I should replace s with s conjugate. So the 2 conjugate becomes same s itself. So x star of t e power minus st dt. So this is our required Laplace transform. And what will be the ROC here? Here again it depends on only the real portion of x of t and real portion of s. So your ROC will remain same. Because the conjugate changes only the imaginary portion, right? So one observation we can make out from here is if x of t is real, then we have x of t equal to x conjugate of t, which also implies x of s is equal to this one, x conjugate of s conjugate. So what it implies is if x of s has zeros and poles at s naught, then what happens? Then my s of s naught will be equal to 0, which is also equal to x star of s naught star. So this implies, taking again conjugate on both sides, I'll get x of s naught star is also equal to 0. So this implies x of s also has zeros and poles at s naught conjugate. So this implies that the poles and zeros come as complex conjugate pairs. This is for real x of t only. So next let us see the convolution property. 7th one. This is again an important property, and everything is straightforward from the Fourier transform. So if x1 of t has Laplace transform x1 of s, ROC equal to r1, and x2 of t has Laplace transform x2 of s with ROC equal to r2, then my x1 of t convolved with x2 of t will have a Laplace transform, which is given by the product of x1 of s and x2 of s, and ROC will contain at least r1 intersection r2, because here also there can be some pole zero cancellation. Again, since they are product, it is straightforward to visualize also. So if we take s plus 1 and this is just s plus 1, if you see if they cancel out, you will get 1 for this, for which the ROC is the entire s plane, right? So that is one good example. So next let us see differentiation in time domain. So differentiation in time domain. So what do we have? If x of t has Laplace transform x of s with ROC equal to r, then my dx of t by dt will have a Laplace transform given by xs of s with ROC at least r. Why? Because if there is a zero or if there is a pole at s at the origin, then if there is only one pole at origin and if that is determining the region of convergence, then that will get cancelled because of this, right? So then my ROC will be extended beyond 0 also. So that way. So for this proof, again it is straightforward. You can get it from the inverse Laplace transform equation. So which is nothing but j minus j infinity sigma plus j infinity x of s e power st ds. So my dx of t by dt, if you take, I can take it inside the integral. So x of s is not affected by d by dt. Only this term will be affected. So d by dt into e power st ds. So this will give me s into e power st. So this is nothing but sigma minus j infinity sigma plus j infinity x of s into s e power st dt ds. So this is what we already got. So now let us see differentiation in the S domain. This everything again we saw in the Fourier transform also. We just have to correlate and learn. And here we need to take care of the region of convergence. So again, if x of t has Laplace transform x of s with ROC equal to r, and then dx of s by ds. So this is nothing but minus dx of t. We'll derive this. But what do you think my ROC will be? So my ROC is actually getting determined by the poles. And when you take the derivative, the poles will not go away. So my ROCs will still be r. Okay. So and I'll also remain with the same pole, same set of poles. Maybe if you take 1 by s plus 2, maybe it will increase to 1 by s plus 2 whole square, right? The pole is getting doubled, but still it is in the same location. So my ROC will still remain the same. So for this proof, like you can take the Laplace transform. So dx of s by ds. Again, you will get this minus t factor. So from that you can get this one. So let us see an example. So we already had the Fourier transform of, the Laplace transform of e power minus at u of t. So its x of s was 1 by s plus a and region of convergence was real of s greater than minus a. So now if I take the derivative, so dx of s by ds, let's call it y of s. Then what will I have? I'll have minus 1 by s plus a whole square. And my real of s is still greater than minus a. And what will be my corresponding y of t be? It will be minus t e power minus at u of t. Right? So my Laplace transform pairs are minus 1 by s plus a whole square. Real of s greater than minus a. If you see, you can actually cancel this minus sign and write t e power minus at u of t. It's nothing but 1 by s plus a whole square. So if you perform another d by ds, what will you get? Here you will get minus t square e power minus at u of t. And on the right hand side, you will get minus 2 by s plus a whole cube. And your region of convergence is still same. So you can again bring this 2 minus, you can cancel and bring this 2 this side. One by s plus a whole cube. So for general case, if you take here, you will just get 3, 4, 5, it will get multiplied. So you can write it as n minus 1 factorial, and this is t power n minus 1 e power minus a t u of t. We'll be having a Laplace transform 1 by s plus a whole power n. You can see a factor of 1 difference. Here it is 3, here it is 2. And your region of convergence is going to be real of s greater than minus a. So this signals also you can encounter frequently, so it is good to know this. So our next property is integration in the time domain. So it is nothing but the reverse of whatever we did here, right? Differentiation and integration. So if my x of t is having x of s with ROC equal to R, then my integral minus infinity to t x of t dt, or we can say x of tau d tau because we have used t here. So this will actually be having a Laplace transform of 1 by s x of s. So now you can see this extra factor of s. So there is a pole at origin. So if this R is such that it is having a, like if it is having origin also in as part of this region of convergence, now that is not possible, right? And usually if you see x of t is nothing but the right-sided signal. Because otherwise it is difficult for it to converge. So if we make these assumptions, then your ROC will be R intersection real of s greater than 0. Okay. So as another derivation, you can also see your u of t convolved with x of t is nothing but this integration. And your u of t has a Laplace transform 1 by s. It is just e power minus a t of t with a equal to 0, if you recall, right? So, and its region of convergence is real of s greater than minus a. Your a is 0, so it is greater than 0. So then your u of t convolved with x of t will actually give you 1 by s x of s. And your ROC is nothing but R intersection real of s greater than 0. So x of t being the right-sided signal is not very strict constraint. Even without this constraint, your ROC will still end up being this one. So again, one point I missed to tell you is in all these things, right, when we take this kind of intersection, it is possible that there can be no region of convergence at all. So in that case, what do we actually say is the Laplace transform does not exist for such a signal. Okay. So next we have the initial value theorem. So this is again a very important theorem, and it is valid only under some specific constraint. So let us see the constraint. So the x of t should be 0 for t less than 0. Okay, so it's like a right-sided signal, or it can be a finite signal. So in that case, your x of 0 plus the initial value of x of t can be found from the Laplace transform. It is nothing but s tends to infinity s x of s. Again, some other constraints are there, which is nothing but x of t should not have any impulses or higher order singularities. So higher order singularity meaning something like d delta of t by dt, something like this, dn at t equal to 0 at origin basically. So in that case, this is valid. So let us actually see the proof of this. So before going to the proof, we'll once again take a look at the differentiation property. So we got dx of t by dt as x of s. So in this derivation, what we have done, we have assumed that x of t is a full signal. It varies from minus infinity to infinity. But in our example, we saw that we want x of t to be equal to 0 for t less than 0. So there is also an additional factor we need to include, which we'll see now. I'll once again derive the dx of t by dt formula. So we have a Laplace transform for x of t as x of s. So this is nothing but x of s is integral 0 to infinity, because it is anyway, x of t is anyway 0 for t less than 0, e power minus st dt. Now my, let's say x prime of s is nothing but dx of t by dt from e minus st dt. And this differentiation we can actually have it from 0 minus. Here also we can have it from 0 minus. 0 minus means it is just before 0. So 0, like from, if you approach it from left, you have 0 minus. If you approach it from right, you have 0 plus. So since we want to also include 0, we are taking it from 0 minus. So now if I apply the differentiation by parts, where u dv is given by uv minus integral v du. So here I will take my u as e power minus st and dv as dx of t by dt into dt. So my v is nothing but x of t and my du is nothing but minus s e power minus st dt, right? So now I can apply this formula. My uv is nothing but e power minus st x of t, and my integrating limits is 0 minus to infinity minus integral v du x of t minus s e power minus st dt, again 0 minus to infinity. So this, if I evaluate at infinity, this term will go to 0. So I'll get 0 minus x of 0 minus of this s, I can take it out. So it is plus s integral 0 minus to infinity x of t e power minus st dt. So this is nothing but x of s. If you see, here it is x of s, right? So my x prime of s is nothing but x of s into s minus x of 0 minus. So if a signal is starting from 0, you need to also include this initial condition. So if it started from infinity, minus infinity, for convergence, we actually require x of minus infinity equal to 0. So this factor will actually go away. So we are getting only x of s. So your dx of t by dt will have the Laplace transform x of s minus x of 0 minus. So if you take another derivative, so what will your Laplace transform be? It will be s square x of s minus sx of 0 minus dx of x by dt evaluated at 0 minus. Okay, because it is like differentiation of this one. So you will get s into sx of s minus x of 0 minus, and that dx of t by dt evaluated at 0 minus. So you will get this term. Okay. So now with this background, we need to prove this statement. Okay. So I'll again take this x of s minus x of 0 minus is nothing but integral minus infinity to infinity, and this is actually 0 minus dx of t by dt e power minus st dt, right? And now if I take limit s tends to infinity, you can see this term will actually go to 0. But it doesn't go to 0 everywhere. Why? Because if I evaluate this at 0, e power minus 0 into infinity I'll get. Infinity into 0, something like this I'll get. So what I'll do, I'll first evaluate this and then apply the limits. So 0 minus to 0 plus dx of t by dt. And in this region, it is just going to be 0 dt, right? So I can neglect this term. Plus integral 0 plus to infinity dx of t by dt e power minus st dt. So now what I'll do, I'll apply the limits. So limit s tends to infinity is x of s minus x of 0 minus. This is nothing but, so this is nothing but x of t from 0 minus to 0 plus, and this term is nothing but e power 0 plus to infinity dx of t by dt into 0 into dt. So this term goes away as total. So with this term, what will I get? I'll get x of 0 plus minus x of 0 minus. So my x of 0 minus I can cancel, and then I'll get x of 0 plus s limit s tends to infinity s x of s. So this is our initial value theorem. And you should also take care of the conditions. Otherwise, this will be different, right? Okay. So my next property is the final value theorem. So we saw the initial value theorem where x of 0 plus the initial value of x of t is dependent on the Laplace transform multiplied with s when we tend s to infinity. So final value theorem is also similar to that. So only the 0 and infinity will change. So for the initial value theorem, we had the constraint saying that there should not be any impulses or higher order singularities at t equal to 0. Similarly, for the final value theorem, we want x of infinity to be finite. So x of t should be finite as t tends to infinity, and the other constant also hold true. X of t should be equal to 0 for t less than 0. So now the final value theorem, so limit t tends to infinity x of t, this is x of infinity, is nothing but limit s tends to 0 s x of s. Okay. So similarly, derivation we can start from here only. Only the limit we are applying to 0. So my s x of s minus x of 0 minus was nothing but integral 0 minus to infinity dx of t by dt e power minus st dt. Now limit s tends to 0, if you can see, this will go to 0. So this will go to 0 and this e power 0 will become 1. So what will I get? Into 1 dt. This is nothing but x of t itself. So this is going to be x of t from 0 minus to infinity. So this is limit t tends to infinity x of t minus x of 0 minus. So this again cancels, and then you will directly get the final value theorem. So you may often expect problems based on these two theorems. So it's good for you to go through these once again. So if you keep them together and compare, you can just see it's just like only the 0 and infinity are changing places. For x of 0, you need to actually tend s to infinity, And for x of infinity, you need to tend s to 0. So that is all with the properties. Now let us quickly see some important Laplace transform pairs. So we would have already worked out through these. I am just summarizing them. So I have the signal, the transform, and the region of convergence. Okay. So the first signal is my unit impulse. So its transform is nothing but 1. Even for the Fourier transform it was 1. And its region of convergence is all S, entire S plane. So my next is u of t. So if you know, this was 1 by S we derived just now. And its region of convergence was real of S greater than 0. And we also have minus u of minus t. So this will again have 1 by S. So through the similar way, right, e power minus at u of minus t with the minus sign, we had 1 by S plus a. And if we tend a to 0, it will just be 1 by a. And here the real of S is actually less than 0. Right? So then my next one is, again we saw this one, u of t. So this one was 1 by S power n, and my region of convergence was same. So opposite to this we have u of minus t. So this one also, it has same Laplace transform, but its region of convergence is different. And we can also see this with the e power minus at u of t. So this was 1 by S plus a, and real of S greater than minus a, minus e power minus at u of t. It was 1 by S minus S plus a, real of S greater than, less than minus a. Right? So then we can have t power n minus 1 by n minus 1 factorial e power minus at u of t. So this is nothing but multiplication by a factor of e power minus at. So that if you go back and see, it is nothing but the property of shifting in the frequency domain. So yeah, shifting in the S domain, we had this factor, we had S minus S naught. Now it is minus, so we'll just need to replace with S plus S naught. So this will be 1 by, this one we have to take, this one, and replace S with S plus A. And your region of convergence will be same. Similarly for this one also, the same technique. So you will get S plus A whole power n, and real of S less than minus A. And if you just add the shifted impulse, delta of t minus t, so you know by the property, if you had shifted impulse, you'll just have e power minus st, right? So this will be e power minus st, and this is a finite number. So your region of convergence will be all S. Which I mean to say is there is no poles in it, right? So your region of convergence is actually the entire S plane. And these are really very important. So your cos omega naught t u of t and sin omega naught t u of t. So this is nothing but e power j omega naught t u of t plus e power minus j omega naught t u of t by 2, right? So this is going to be 1 by 2 into 1 by S plus j omega naught plus, here it will be S minus j omega naught, and here it will be 1 by S plus j omega naught. It is just like e power minus at u of t. A is replaced with j omega naught and minus j omega naught. So what will this turn to? So this will be nothing but 1 by 2 into, you will get 2 j omega naught omega naught will cancel. You will get 2s in the numerator, and denominator you will get s square plus omega naught square. So your transform is going to be s by s square plus omega naught square. And you can see your region of convergence is real of s greater than 0, because real of a is here 0, right? So it should be greater than minus a, and real of a is actually 0. So it is real of s greater than 0. Similarly for sine omega naught t u of t. So this is nothing but e power j omega naught t u of t minus e power minus j omega naught t u of t by 2j. So here I have 1 by 2j into 1 by s minus j omega naught minus 1 by s plus j omega naught. So if you take the LCM and cross multiply, you will remain with 2j omega naught by s square plus omega naught square. So your 2j factor goes away, you get omega naught by s square plus omega naught square. So here the numerator is s, here it is omega naught, but the denominator is same, which means they have poles at the same location. And additionally, this cos omega naught t has a 0 at s equal to 0 at origin. And here also your real of s is greater than 0. Now the same thing, if we have a multiplication by e power a t u of t, it is just a decaying cosine function, right? Decaying cosine signal. So what you have to do? You have to replace s with s plus a. So it will be s plus a by s plus a whole square plus omega naught square, and your real of s is greater than minus a here. Similarly, for sine omega naught t e power minus a t u of t, you have 1 omega naught by s plus a whole square plus omega naught square, and your region of convergence is same. And you have something called as u minus n of t given by u of t convolved with u of t n times. So one convolution will give a factor of 1 by s, right? So 2, if they are convolved, it will be 1 by s square. So if there are n convolution, you will get 1 by s power n. And your region of convergence, real of s greater than 0. And you can also define un of t, which is nothing but the derivative of the delta function or the unit impulse. Nth derivative of the unit impulse. So these are also class of singular functions. Why? Because delta of t itself is infinity at t equal to 0. If you take derivative of that, it is again grow up like very rapidly. But this is also like mathematical constructs only. So if you see this, it is going to be, so since it is differentiation, it will be multiplied s power n times into 1. So this is going to be s power n. And your region of convergence is all s. So our importance here is with rational Laplace transforms. So if you see here, all these are like rational Laplace transforms, right? These can be like zeros at s equal to 0, poles at s equal to 0. This is like some denominator having s plus a whole square plus omega naught square, those kind of things. And this is simple s square plus omega naught square denominator. And we also have s plus a kind of denominator, right? So using these, actually we can find the inverse Laplace transform for rational Laplace transforms, right? So these pairs are really very important, and it is good if you derive them once and get to know them. And as you practice and like without seeing the table, if you're able to derive them and arrive at them when you're solving the questions, you will actually able to remember them also in future for a long time. So I recommend you to just verify, just derive and verify if your answers are coming correct. And then from next time onwards, you just keep deriving. Do not look at this table. Okay. So that's it for today. I'll see you guys in the next video. Until then, take